For our fourth video, we're going to talk about the different types of physical properties that can be used to identify one mineral from another. In our first video, we talked about the defining characteristics, those 5 properties that something has to have to be considered a mineral. But in this video, we're going to focus on the physical properties of minerals. And because minerals have that definitive crystalline structure, the way those atoms repeat the way that they're bonded in specific shapes, and the fact that they have fixed chemical compositions, minerals are very unique from one mineral to another. Each mineral has very unique both physical and chemical properties to them. So it's really important to be able to identify minerals, to be able to tell them apart from one another. And in order to identify a mineral, the diagnostic properties are going to be what's most important. Minerals also have ambiguous properties. These are properties that don't really help us define what this mineral could be because several minerals share the same ambiguous properties. But one of the properties that is diagnostic that's helpful to look at when we're trying to identify a mineral is called luster. And luster is just the way that light is reflected off of a surface. And there are literally dozens of different types of lusters out there. But the main 2 that we're going to focus on in this course are metallic and non-metallic lusters. Minerals that have a metallic luster look very shiny. They look like a small piece of metal, like something we would want to have jewelry made out of. We can also have a submetallic luster, which is just a subtype of metallic. It's still shiny, but it's not quite as shiny. It's a little bit duller. But our second major type of luster is non-metallic. This is where it does not look metallic at all. Instead, it might look like a piece of glass, it might look like a pearl, it might look like sediment. But it's not shiny. It doesn't reflect light very well. So we call it a non-metallic luster. But one of the first properties you might think about when you look at a mineral is what color. Here we're looking at 5 different minerals with very different colors to them. But colors is one of those ambiguous properties that does not help us identify a mineral. And that's because it's not diagnostic. If we have really small impurities inside of the chemical arrangement inside of that atom, if we just throw in one wrong atom inside of the millions inside of it, it's going to lead to an impurity, which can drastically change the color. So even though color is probably the first thing we notice when we look at a mineral, it is the least helpful thing when identifying it. So we want to completely disregard the overall color of the mineral completely when we're trying to identify it. It's an ambiguous property. We don't care about it. One aspect of color that we do care about when it comes to minerals, though, is the mineral streak. And the streak is just the color of the powder that's left behind if we're capable of rubbing away the surface of the mineral. You might think that if we have a piece of gold-colored mineral, that when we rub it and we can powder the surface, that powder would be gold as well. But what makes minerals unique is the fact that the color of the powdered mineral can be totally different than what it looks like on the surface. So here, this gold-colored mineral, when we powder it, leaves a black powder behind. And that black powder is called its streak. Unlike the gold overall color that's ambiguous and unimportant, that black streak is a diagnostic property. It can help us identify the mineral. And for the most part, we see that metallic minerals, the ones that are shiny and reflect light well, generally have a much darker colored streak than non-metallic minerals, the ones that don't reflect light or look like a metal. And in addition to all of that, not all minerals produce a streak. If we're looking at a mineral that is really, really hard or resistant to breaking, we're not going to be able to create a powder from it at all. And our last optical property that we want to look at when it comes to identifying a mineral is how well does light go through or transmit through that mineral. Some minerals are opaque, like this window on the far right. Here, it's not going to allow any light through whatsoever. It would be like a solid wall. But some minerals are translucent. This means it's going to allow the light to come through, but it's not going to allow an image to come through. So think about a bathroom window. Hopefully, if you have a bathroom window, it's going to allow the light to come through, but it's not going to allow people outside to see what you're doing in the bathroom. It's going to obscure your image, kind of blur it in some way, while allowing the light to get inside. This is called translucent. And we also have some minerals that are totally transparent. This would be like a normal window. We're going to be able to allow light to move through it as well as an image. We're going to be able to see what's going on outside of that window as well. So minerals can either be opaque, not allowing light or an image. They can be translucent, allowing light but no image. Or they can be transparent, where they allow both light and an image to pass through the mineral. But now we're going to look at the overall shape or the habit of the mineral. And this is just where we see that repeating atomic arrangement showing up and building into the overall shape or habit that this crystal will ideally grow into. But unfortunately, a lot of the times minerals do not have the capabilities of growing into this crystal habit or this ideal crystal shape. Something is going to obscure the path of that crystalline lattice and make it take a slightly different shape overall. So there are physical properties that we want to look at in our mineral identification as well. And these are going to be things like mineral hardness, cleavage or fracture, and tenacity. So overall, the strength of a mineral, how resistant it is going to be entirely determined by the types of chemical bonds inside of it. And the strength of the minerals is going to determine how that mineral either responds to stress or breaks under stress. So one of the first things we want to look at when we're trying to identify a mineral is how hard it is. How resistant is it to scratching? And this is probably the most important diagnostic tool when we're trying to identify minerals. And we can fairly easily identify how hard a mineral is by using what we call the Mohs hardness scale. And this scale ranges from 1 to 10, where 1 is a soft mineral and 10 is the hardest mineral. And by trying to scratch minerals with different common substances, like our fingernail or a penny or a piece of glass, we can figure out exactly how hard that mineral is. Again, with higher hardness values leading to harder, more resistant minerals, and lower hardness values leading to softer, easily broken minerals. But the physical strength properties that students always seem to struggle with, and that I honestly struggled with for a couple years in undergrad myself, was the difference between cleavage and fracture in a mineral. And both of these terms is how a mineral is going to respond to stress. When it breaks, how does it break? So minerals generally either have cleavage or they have fracture. They generally don't have both. And cleavage is what happens when a mineral breaks, but there are weak chemical bonds inside of that mineral. So when the mineral breaks, it breaks along those weak chemical bonds, and it's going to lead to flat, smooth planes or surfaces on that mineral. So here on the upper image, we're seeing these kind of like skewed cubes. This is cleavage. It's a mineral called calcite, and if I took a hammer to this, each broken piece of it is going to have this exact same shape. because it has weak chemical bonds that when the mineral breaks, it's going to break along those weak bonds, always forming this exact same shape. And this is known as cleavage. The bottom example is showing us what's called planal or basal cleavage. Here, we still have minerals that as we break it, it will always break into the exact same shape along those weak chemical bonds. But here, these are going to be like pages within a book. I'm going to be able to peel it apart layer by layer. But not all minerals have weak atomic bonds inside of their crystalline lattice. We're going to see that some minerals only have really strong chemical bonds. So instead of them having cleavage when they break, instead they're going to have fracture. And fracture, most of the time we see an irregular fracture. If I were to drop a plate in my kitchen tonight, it's going to break into dozens of pieces, each of its own different shape. It's probably going to have really jagged, sharp edges along it. That's fracture, or an irregular fracture, I should say. But there's a second type of fracture that's common that's called a conchoidal fracture. And this we can see on the right part of this image. You'll see that there's like a smooth dip on the surface of this mineral, and that's its conchoidal fracture. If you've ever broken a glass instead of a plate, and the bottom of the glass breaks off and there's a nice smooth dip inside of it, that's a conchoidal fracture. So again, minerals generally either have cleavage or they have fracture. If there are some weak atomic bonds inside of that mineral, we're probably going to see cleavage, where it's going to break into smooth, flat sides. But if the mineral does not have any weak chemical bonds, instead it's going to have fracture. It's either going to have irregular fracture, like a plate breaking into whatever shape with jagged edges, or like my glass, it's going to break with a conchoidal fracture, having a very smooth dipping break inside of it. The final physical property that all minerals have are density and specific gravity. Density is just basically how much does something weigh for its given size. And specific gravity is very closely related to the density. We're going to see that we can quickly measure the specific gravity of minerals by holding them in our hands. If we have two minerals that are roughly the same size, one might feel heavier than the other. The one that feels heavier is going to have a higher specific gravity. And that's because the atoms are more densely packed. Even though it's the same size, it weighs more because it has more atoms densely packed inside of it, leading to a higher specific gravity. And generally, we see that our metallic minerals, the ones that are reflecting light and conducting electricity, have a much higher specific gravity than our non-metallic minerals do. And finally, there are some properties that are kind of dead giveaways to what minerals we're trying to identify. And we just call these special properties. Some minerals have very specific tastes. If I gave you the mineral halite and you licked it, it's going to be incredibly salty because halite is our table salt. We also see that some minerals have very specific feels to them. So for example, graphite is very greasy. If you're left-handed and you've ever written with a pencil, you know that feeling of the grease that's left on your hand after you finish writing. Some minerals have very specific smells. Sulfur smells like rotten eggs, so it's not a very pleasant mineral to be around. Other minerals have magnetism. These are things that magnets are attracted to, kind of like the sides of our fridge. And this is generally because the mineral has iron inside of them. Some minerals have optic properties. It changes the image when light moves through them. And one of my favorite examples is called double refraction, which we see here on the bottom right. Calcite causes double vision when an image moves through it, called double refraction. It's doubling that image. But calcite also has one more special property called effervescence. And this is my favorite thing ever. So I'm probably going to ask you about this on a quiz and most definitely on an exam. Calcite has this special property called effervescence, where if we add acid to it, the surface of that calcite is going to bubble up, releasing all of the carbon dioxide stored inside of it.